You're good? Okay. Normally you say like action or something like that. That's all right. Okay, so we're gonna do this. We're gonna see if the limit, oh sorry, we're not limiting yet. The integral from 0 to infinity of e to the negative x squared, is that convergent? Notice we're just asking if it's convergent or not. We're not looking for a value. Imagine if you tried to integrate that. That is gonna be kind of tough to do. So what we're gonna do instead is we're gonna compare this function right here to a different function. So the function that I'm going to compare it to is e to the negative x. And I just want you to note the relationship between e to the negative x squared and e to the negative x. What's the relationship between these two functions? Well, here, let's consult GeoGebra for a minute. So here I have two different graphs. The one in red is e to the negative x, and the one in green is e to the negative x squared. Is that coming through clear? Hopefully it is. Now here's the thing. We're going from 0 to infinity. Notice that from 0 to 1, maybe I'll bring this down a bit. From 0 to 1, which one is greater? It's e to the negative x squared is greater than e to the negative x. But here's what's important. Starting at 1 and from then on, it's the other way around. E to the negative x is greater than e to the negative x squared. Why do we care about that? Well, let's talk about a couple of things. So let me finish this thought. E to the negative x squared is less than e to the negative x for x greater than 1. Well, first of all, you might ask, wait, we're going from 0 to infinity, not 1 to infinity. Well, let me just point out that from 0 to 1, e to the negative x squared, is that going to be convergent or divergent? Well, look at e to the negative x squared from 0 to 1. It's not an infinite area. It's a finite area. I didn't even need that word. I'll get back to that. So this right here, all we care about is convergence or divergence. It converges, okay? Since it's a finite area over there. So instead, we're gonna pay attention to this. We're gonna really pay attention to the integral from 1 to infinity of e to the negative x squared. Okay? So this right here, if we were to compare this to the integral of e to the negative x, what's the relationship there? Hopefully you'll see that this area is going to be less than this area, e to the negative x dx. Hopefully you agree with that statement right there. Why? Because of this statement we made over here. That function is less than this one from x greater than 1, so this must be true as well. Okay, and let's see, let's focus on that integral over there. Let's focus on the integral from 1 to infinity, e to the negative x dx. Well, we know we need to take the limit as t approaches infinity, 1 to t, x dx. So then this is going to be for negative e to the negative x. We integrate and we're going from 1 to t. So this becomes negative e to the negative t minus negative, so plus e to the negative 1. So what does this do? As t goes to infinity, what does negative e to the negative t do? Well, this is going to negative infinity, so it's essentially negative 1 over e to the t. So this part right here is going to 0. So all of this is really just equal to e to the negative 1, or 1 over e. And that means that this function right here converges. So if you've got a function that converges, and you're trying to compare it to another function that's less than this one right here, then this other one must converge as well. So again, if this red function, this red line, if that converges, then the green one must converge as well, since the green one's always less than the red one. And that leads us to, if you take out that worksheet that I had passed out on Monday, that worksheet looked like this. So let's note down some facts. And by the way, this is from the book as well. And this is page 550 out of the book. And we're basically working with what's called the comparison theorem. The comparison theorem starts like this. If you've got f and g continuous functions, f of x is greater than or equal to g of x, which is greater than or equal to 0, for x greater than or equal to a. So that means at some point, for some x greater than or equal to a. In our problem over there, it was x greater than or equal to 1. So this is what we can say. Either one of two things is going to happen. We're going to say that if the integral from a to infinity of f of x dx is convergent, then, let me write it underneath, sorry. Then we're going to compare that to the integral from a to infinity of g of x dx.
I just need to
Yeah. So if, remember, g of x is less than f of x. F of x, this integral right here is convergent, so that means a smaller function will also be convergent. Now let's go the other way. Let's say we've got the integral from a to infinity of g of x dx. What do you think we're going to say about this? We're going to say if this is divergent, then maybe you can already anticipate what we're going to say here. This integral, again, remember, f of x is greater than g of x. So if g of x, this integral of g of x is divergent, and f of x is a bigger function, then in theory, this area here should be greater even than this area. So if this area is greater than this area, then this must also be divergent. Again, that's on page 550, as well as this example as well, if you want to take a look at it. All right, thanks.